In problem 6, we're given the equation for a polynomial kernel, and we're asked several questions. The first question is, which of these lifting functions corresponds to the polynomial kernel when we're dealing only with one dimension? And there are a couple of ways to arrive at the answer. The first way, which is the official solution, is to expand the polynomial kernel. So this becomes 1 plus 2xi xj plus xi squared xj squared. And then we can compute the inner product of phi xi by phi xj for each of these options and see which one of them equals the expanded version of our polynomial kernel equation. And let's look at that. So again, this is the official solution. This is the expanded version of the polynomial kernel. And then when you choose option C and do the inner product of this vector by itself, you get 1 plus square root of 2xi times square root of 2xj, which is this, plus xi squared xj squared, which is this, and this simplifies to this, which turns out to be identical to the expanded version of our polynomial kernel equation, so C is the correct answer. Moving on to part B, or part 2, we're given a data set with 3 data points, x1 being -1, x2 0, x3 1, and each point has a label, red, blue, and red respectively. And we want to know whether when this data set is lifted by the polynomial kernel, whether it will be linearly separable. So let's look at that solution. So again, this is our data set. We have x1 equal to -1 with a red label, x2 equal to 0 with a blue label, and x3 equal to 1 with a red label. And we want to know, we know that they are not separable in the original space as seen on this plot. We want to know if they're separable in the lifted space. So we have the lifting function. We have decided this is the correct lifting function, and all that needs to be done is substitute the value of x for each of the data points and see what the lifted vector looks like. So when x1 is -1, we end up with this vector as our lifted version of x1, and we know it has a red label. And when x2 is 0, we end up with this vector as the lifted version of x2 with a blue label, and this as the lifted version of x3 with a red label. So notice that our lifted space is 3-dimensional, 1, 2, 3, but the first dimension is all 1, so we can ignore that and focus on the second dimension, which is -√2, 0, square root of 2, and the third dimension, which is 1, 0, and 1. And we can plot these 2 dimensions, the second dimension against the third dimension, or the third dimension against the second dimension, and visualize it. And in fact, we see that we end up with this plot. This is our second dimension, which is -√2, 0, square root of 2. And this is our third dimension, which is 1, 0, 1. And we apply the given labels to each of these data points, and we see that they are, in fact, now separable across the third dimension in the lifted space. So the answer to part B is yes, they are separable when lifted by the polynomial kernel. So moving on to the third part, now that we know that this data set is separable, we want to see what the decision boundary looks like, what the nonlinear decision boundary looks like. And for any nonlinear decision boundary defined by any kernel, whether it's polynomial or radial or whatever, it has to satisfy this equation where a0 and a tilde are weights. If specifically a0 is one weight and a tilde is a vector of weights, each of which corresponds to a value of each data point. So x1 tilde corresponds to alpha 1 tilde corresponds to alpha 1, alpha 2 tilde corresponds to x2, etc. And this sums over all the data points in our data set, in this case 3 data points. So we're given several options, and the question is which one of these options for alpha 0 and alpha tilde provides a valid equation corresponding to our nonlinear decision boundary. And we can go through these and figure it out. The first step is to substitute the equation for the polynomial kernel into that formula, and we end up with this. And the second step is to expand this sum. Well, how do we expand it? Well, it's easy. We have the values of xi, that is x1, x2, and x3 in our data set. And we just substitute in here and expand the sum. So this becomes alpha 0 plus, when I is equal to 1, we get alpha 1 tilde times 1 plus x1. Well, x1 is negative 1, so it becomes 1 minus x squared. So that's that term here. When I equals 2, this becomes alpha 2 tilde, and this becomes 1 plus 0 times x, so this whole term is 1, so that just reduces to alpha 2 tilde. When I equals 3, this becomes alpha 3 tilde times 1 plus 1 times x, so it reduces to this term here. So this is the equation for which we have to find the appropriate weights to define our nonlinear decision boundary. Well, again, in the options to the question, we're given a set of weights, and we have to determine which one of these provides a valid equation. Well, in option A, we're given alpha 0 equals 1, alpha 1 tilde is 1, alpha 2 tilde is 0, alpha 3 tilde is 1. When we substitute those weights in this equation, we end up with this equation for f of x. And the question is this solvable for a real value or real values of x? And the answer is no, it's not, because this reduces to x squared equals negative 3/2, and we know that when a square is negative, then there is no real value of x that satisfies this equation. So A is not a valid option for a set of weights that would satisfy this equation. In the same way, C, this set of weights, this being alpha 0 and this being alpha tilde, does not satisfy that equation because it gives us x squared equal to a negative number. Again, there's no real value of x that satisfies this. But option B, where alpha 0 is negative 3 and alpha tilde are these numbers, when we substitute them in this equation here, we end up with x squared equals half, and that is solvable. So x equals plus or minus 1 over square root of 2 does provide a valid decision boundary in the original dimension, and the classifier in the original dimension would be absolute value of x is greater than 1 over square root of 2 or less than 1 square root of 2, and that classifier is a nonlinear classifier that is able to separate these data points. But we can take this one step further and actually visualize the classifier in the lifted data space. So again, we have this as our equation with the set of generic weights. And now that we have decided that the weights provided in option B are valid weights, we can just substitute them in this equation, and we end up with this function as our classifier in the lifted space. And so for each value of x in the data set, we can put it in here. And if x is blue, we want f of x to fall on one side of 0. And if x is red, we want it to fall on the other side of 0. And that's how we would separate it separate the data in the lifted space. Let's see if that actually works. So for the first data point, x1 equals -1, the lifted version becomes equal to 1, and that's a red point. That's this point over here. Here I'm plotting x against the lifted version, f of x. When x2 is equal to 0, f of x2 becomes equal to -1, and that's this blue point over here. We know the label of that point is blue. And for x3, we end up with this point. So in fact, in the lifted space, this classifier does separate our red points from our blue points across the decision boundary 0 in the lifted space.